Hello viewers, I welcome you all to the topic on food chemistry. Today's episode will be on functional properties of proteins. To begin with introduction, proteins are the macromolecules which play a fundamental role not only in sustaining life but also in foods derived from plants and animals. In addition to their contribution to the nutritional properties of foods through provision of amino acids that are essential to human growth and maintenance, proteins impart the structural basis for various functional properties of foods. Proteins are the principal structural and functional components of many food systems. Example, meat, cheese, gelatin, egg white and many cereal products. In addition, proteins are used to fabricate and facilitate the engineering of new foods such as protein beverages and extruded foods. The application upon the physico-chemical properties of protein ingredients collectively referred to as the functional properties. Proteins as dry powders have very limited appeal to potential users or consumers. To facilitate their use in foods and their conversion to desirable ingredients, they must possess appropriate functional properties following interactions with other food components, example water, carbohydrates or lipids during processing. Functional properties of foods are those physico-chemical properties which affect their behavior in food systems during preparation, processing, storage and consumption, and also contribute to the quality and organoleptic attributes of food systems. Therefore, functional properties of proteins can be studied under following subtopics. First is introduction to functional properties, second is organoleptic properties, third is protein hydration, fourth solubility of proteins, fifth gelation, sixth binding, seventh emulsifying and foaming properties, eighth is other properties which include sedimentation, denaturation and amphoterism, and last conclusion. To begin with, introduction to functional properties. Functionality of food proteins is defined as those physical and chemical properties which affect the behavior of proteins in food systems during processing, storage, preparation and consumption. Food preferences by human beings are based primarily on sensory attributes such as texture, flavor, color and appearance. The sensory attributes of a food are the net effect of complex interactions among various minor and major components of the food. Proteins generally have a greater influence on the sensory attributes of foods. For example, the sensory properties of bakery products are related to the viscoelastic and dough-forming properties of wheat gluten. The textural and succulence characteristics of meat products are largely dependent on muscle proteins. Example, actin, myosin and several water-soluble meat proteins. Textural and curd-forming properties of dairy products are due to the unique colloidal structure of casein micelles, and the structure of the cakes and the whipping properties of dessert products depend on the properties of egg white proteins. The physical and chemical properties that govern protein functionality include size, shape, amino acid composition and sequence, net charge and distribution of charges, hydrophobicity or hydrophilicity ratio, secondary, tertiary and quaternary structures, molecular flexibility or rigidity, and ability to interact or react with other components. The general functional properties of the proteins is as shown on the screen. The various functional properties of proteins can be viewed as manifestation of three molecular aspects of proteins. First is the hydrodynamic properties, second is the protein-protein interactions, and the third is protein surface related properties. The functional properties such as viscosity, thickening, gelation and texturization are related to the hydrodynamic properties of proteins, which depend on size, shape and molecular flexibility. Properties such as wettability, dispersibility, solubility, foaming, emulsification and fat and flavor binding are related to the chemical and topographical properties of the protein surface. Functional roles of food proteins in food system is as shown on the screen. organoleptic properties. The organoleptic or the sensory properties of proteins include color, flavor, taste and odor. The sensory attributes of foods are achieved by complex interactions among various functional ingredients. To begin with, protein hydration. Water is an essential constituent of foods. The rheological and textural properties of foods depend on the interaction of water with other food constituents, especially with macromolecules such as proteins and polysaccharides. Water modifies the physicochemical properties of proteins. Water molecules bind to several groups in proteins. These include charge groups, backbone peptide groups, amide groups and non-polar residues. Many functional properties of proteins such as dispersibility, wettability, swelling, solubility, thickening or viscosity, water holding capacity, gelation, coagulation, emulsification and foaming depend on water-protein interactions. Now let us know about water binding and water holding capacity of proteins. The water binding capacity of proteins is defined as the grams of water bound per gram of protein when a dry protein powder is equilibrated with water vapor at 90 to 95% relative humidity. The water binding capacities is also called hydration capacity, whereas water holding capacity refers to the ability of protein to imbibe water and retain it against gravitational force within a protein matrix such as protein gels. The hydration capacity of a protein is related to its amino acid composition. Greater the number of charged residues, greater is the hydration capacity. Several environmental factors such as pH, ionic strength, type of salts, temperature and protein conformation influence the water binding capacity of proteins. Proteins exhibit the least hydration at their isoelectric pH, whereas enhanced protein-protein interactions results in minimal interaction with water. Above and below the isoelectric pH, because of the increase in the net charge and the repulsive forces, proteins swell and bind more water. In food applications, the water holding capacity of a protein preparation is more important than the water binding capacity. Studies have shown that the water holding capacity of proteins is positively correlated with water binding capacity. The ability of a protein to entrap water is associated with juiciness and tenderness of meat products and desirable textural properties of bakery and other gel type products. Next is solubility of proteins. Protein solubility is variable and is influenced by the number of polar and apolar groups and their arrangement along the molecule. Generally, proteins are soluble only in strong polar solvents such as water, glycerol, formamide, dimethylformamide or formic acid. In less polar solvents such as ethanol, proteins are rarely soluble. Example, prolamines. The solubility in water is dependent on pH and on salt concentration. Effect of pH. At low ionic strengths, the solubility rises with increase in ionic strength. Effect of salt concentration. Protein solubility is decreased, that is salting out effect at higher salt concentrations due to the ion hydration tendency of the salts. At low concentrations, they increase the solubility, that is salting in effect, by suppressing the electrostatic protein interaction, that is binding forces. The solubility of a protein is the thermodynamic manifestation of the equilibrium between protein-protein and protein-solvent interactions. Protein-protein plus protein-solvent is in equilibrium with protein-solvent complex. The major interactions that influence the solubility characteristics of proteins are hydrophobic and ionic in nature. Hydrophobic interactions promote protein-protein interactions and result in decreased solubility, whereas Ionic interactions promote protein-water interactions and result in increased solubility. Based on solubility characteristics, proteins are classified into 4 categories. First one is albumins, second is globulins, third is glutelins, and fourth is prolamines. Albumins are those that are soluble in water at pH 6.6. Example, serum albumin, oval albumin, and lactalbumin. Second is the globulins. Globulins are those that are soluble in dilute salt solutions at pH 7. Example, glycinin, fasolin, and lactoglobulin. Third one is glutelins. Glutelins are those that are soluble only in acid pH 2 and alkaline pH 12 solutions. Example, wheat glutelins. And the last one is the prolamines, that are those soluble in 70% ethanol. Example includes zein and gliadins. Both prolamines and glutelins are highly hydrophobic proteins. Generally, solubility of proteins is influenced by several solution conditions such as pH, ionic strength, temperature, and the presence of organic solvents. The next important property is gelation. A gel is an intermediate phase between a solid and a liquid. Technically, it is defined as a substantially diluted system which exhibits no steady state flow. It is made up of polymers cross-linked via either covalent or non-covalent bonds to form a network that is capable of entrapping water and other low molecular weight substances. Protein gelation refers to transformation of a protein from the salt state to a gel-like state. This transformation is facilitated by heat, enzymes, or divalent cations under appropriate conditions. All these agents induce formation of a network structure. Most food protein gels are prepared by heating a protein solution. In this mode of gelation, the protein in a salt state is first transformed into a progel state by denaturation. The progel state is usually a viscous liquid state in which some degree of protein polymerization has already occurred. This step causes unfolding of the protein and exposure of a critical number of functional groups such as hydrogen bonding and hydrophobic groups, so that the next stage, that is formation of protein network, can occur. Proteins form 2 types of gels, namely coagulum, that is opaque gels, and translucent gels. The type of gel formed by a protein is dependent on its molecular properties and solution conditions. The next important property is binding properties of proteins. Proteins can hold together a combination of ingredients. When heated, proteins coagulate so that the product is unbroken. Example is cakes and burgers. Proteins themselves are odorless. However, they can bind flavor compounds and thus affect the sensory properties of proteins. Several proteins, especially oil seed proteins and whey protein concentrates, carry undesirable flavors which limits their usefulness in food applications. These off flavors are due mainly to aldehydes, ketones, and alcohols generated by oxidation of unsaturated fatty acids. Upon formation, these carbonyl compounds bind to proteins and impart characteristic of flavors. The binding affinity of some of these carbonyls is so strong that they resist even solvent extraction. The flavor binding property of proteins also has desirable aspects because they can be used as flavor carriers or flavor modifiers in fabricated foods. This is particularly useful in meat analogues containing plant proteins where successful simulation of a meat-like flavor is essential for consumer acceptance. In order for a protein to function as a good flavor carrier, it should bind flavors tightly, retain them during processing, and release them during mastication of food in the mouth. However, proteins do not bind all flavor compounds with equal affinity. This leads to uneven and disproportionate retention of some flavors and undesirable losses during processing. The next property is emulsifying and foaming properties. Emulsions are dispersed system of one or more immiscible liquids. They are stabilized by emulsifiers, that are the compounds which form interface films and thus prevent the dispersed phases from flowing together. Proteins are amphiphilic molecules and they migrate spontaneously to an air-water interface or an oil-water interface. This spontaneous migration of proteins from a bulk liquid to an interface indicates that the free energy of proteins is lower at the interface than it is in the bulk aqueous phase. Protein stabilized foams and emulsions are more stable than those prepared with low molecular weight surfactants, and because of this, proteins are extensively used in food applications. Although all proteins are amphiphilic, they differ significantly in their surface active properties. The differences in surface activity are related primarily to differences in protein conformation. The conformational factors of importance include stability or flexibility of the polypeptide chain, ease of adaptability to changes in the environment, and distribution pattern of hydrophobic and hydrophilic groups on the protein surface. All of these conformational factors are interdependent and they collectively have a large influence on the surface activity of proteins. Desirable surface active proteins should have three attributes. First one is ability to rapidly adsorb to an interface. Second is the ability to rapidly unfold and reorient at an interface. And third one is ability to interact with the neighboring molecules and form a strong cohesive viscoelastic film that can withstand thermal and mechanical motions. Now let us go to the functional role in foods. Several natural and processed foods such as milk, egg yolk, coconut milk, soya milk, butter, margarine, mayonnaise, spreads, salad dressings, frozen desserts, frankfurter, sausages and cakes are emulsion type products where proteins play an important role as an emulsifier. In natural milk, the fat globules are stabilized by a membrane composed of lipoproteins. When milk is homogenized, the lipoprotein membrane is replaced by a protein film comprised of casein micelles and whey proteins. Homogenized milk is more stable against creaming than in natural milk because the casein micelle whey protein film is stronger than the natural lipoprotein membrane. The emulsifying properties of food proteins are evaluated by several methods such as size distribution of an oil droplets formed, emulsifying activity, emulsion capacity and emulsion stability. The properties of protein stabilized emulsions are affected by several factors. These include intrinsic factors and extrinsic factors. Intrinsic factors. These include pH, ionic strength, temperature, presence of low molecular weight surfactants, sugars, oil phase volume, type of proteins and the melting point of the oil used. Extrinsic factors. These include type of equipment, rate of energy input and rate of shear. Now let us begin with foaming properties of proteins. Foams consist of an aqueous continuous phase and a gaseous that is air dispersed phase. The foaming property of a protein referred to its ability to form a thin tenacious film at gas liquid interfaces so that large quantities of gas bubbles can be incorporated and stabilized. Foams are dispersions of gases in liquids. Proteins stabilize by forming flexible, cohesive films around the gas bubbles. During impact, the protein is adsorbed at the interface via hydrophobic areas. This is followed by partial unfolding, that is surface denaturation. The reduction of surface tension caused by protein adsorption facilitates the formation of new interfaced and further gas bubbles. The partially unfolded proteins associate while forming stabilizing films. The ideal foam forming and foam stabilizing protein is characterized by a low molecular weight, high surface hydrophobicity, good solubility, a small net charge in terms of the pH of the food, and easy denaturability. Protein stabilized foams are formed by bubbling, whipping or shaking a protein solution. Foaming properties of proteins are evaluated by foaming capacity and foaming stability. Foaming capacity. Foaming capacity or foaming ability of proteins refers to the amount of interfacial area that can be created by the protein. It can be expressed in several ways, such as or foaming power, that is foam expansion, or overrun, that is called steady state foam value. Functional role in foods. In several processed foods, protein function as foam forming and foam stabilizing components. For example, in baked goods, sweets, desserts, whipped cream, ice cream, cakes, meringue, bread, souffles, mousses, and marshmallow. The unique textural properties and mouthfeel of these properties stem from the dispersed tiny air bubbles. Several environmental factors such as pH, salts, sugars, protein concentration, lipids, etc. affect the foam formation and stability. Now let's go on to the other properties of proteins. Under this subtopic, we will be learning about other important properties of proteins, which are as follows. Sedimentation. Sedimentation is the tendency for the particles in suspension to settle out of the fluid in which they are entrapped and come to rest against a barrier. This is due to their motion through the fluid in response to the forces acting on them. These forces can be due to gravity, centrifugal acceleration, or electromagnetism. Sedimentation of proteins is carried out to separate them or purify them. Several thousand proteins have been purified in active form on the basis of solubility, size, charge, and specific binding affinity. Usually, protein mixtures are subjected to a series of separations, each based on a different property to yield a pure protein. At each step in the purification, the preparation is assayed and the protein concentration is determined. Substantial quantities of purified proteins are needed to fully elucidate their three-dimensional structures and their mechanism of action. A variety of separation techniques are used to purify proteins, which include salting out, dialysis, gel filtration chromatography, ion exchange chromatography, affinity chromatography, high pressure liquid chromatography, gel electrophoresis, etc. The next important property is denaturation. Denaturation is a phenomenon that involves transformation of a well-defined folded structure of a protein formed under physiological conditions to an unfolded state under non-physiological conditions. The native structure of a protein is the net result of various attractive and repulsive interactions emanating from various intramolecular forces as well as interaction of various protein groups with surrounding solvent water. However, native structure is largely the product of the protein's environment. Any change in its environment, such as pH, ionic strength, temperature, solvent composition, etc., will force the molecule to assume a new equilibrium structure. Subtle changes in structure which do not drastically alter the molecular architecture of the protein are usually regarded as conformational adaptability, whereas major changes in the secondary, tertiary and quaternary structures without cleavage of backbone peptide bonds are regarded as denaturation. Many biological active proteins lose their activity upon denaturation. In the case of food proteins, denaturation usually causes insolubilization and loss of some functional properties. In some instances, however, protein denaturation is desirable. Example, thermal denaturation of trypsin inhibitors in legumes markedly improves digestibility and biological availability of legume proteins when consumed by some animal species. Partially denatured proteins are more digestible and have better foaming and emulsifying properties than native proteins. Thermal denaturation is also a prerequisite for heat-induced gelation of food proteins. The next property is amphoterism. The ability of a chemical to behave both as an acid or base is called amphoterism, and the substance is called amphoteric substance. These substances act as acids in the presence of bases and vice versa. Examples of amphoteric substances include water, amino acids, and proteins. Proteins are amphoteric polyelectrolytes, that is, they possess both acidic and basic properties. The acid-basic properties of amino acids are primary due to occurrence of alpha amino and alpha carbonyl groups, that is, acid-base pairs in them. The amphoterism of proteins is due to the acid-base groups of side chain radicals of protein constituting amino acids. Finally, concluding with the conclusion of the functional properties, I conclude that proteins represent the most important class of functional ingredients because they possess a range of dynamic functional properties. The functional properties of food proteins affect behavior in food systems and influence the quality attributes such as structure, texture, mouthfeel, and flavor of the final product. Therefore, knowledge of the physicochemical characteristics required for particular use is very important. They show versatility during processing, they can form networks and structures, and they provide essential amino acids, that is, they fulfill functional and nutritional requirements. In addition, they interact with other components and improve quality attributes of foods. The functional properties of proteins are often affected by protein solubility, and those most affected are thickening, foaming, emulsifying, and gelling. Insoluble proteins have very limited uses in food. Thank you.